Good morning, students. I'm going to continue my talk on process synchronization from where I had left in the last class. Let us quickly recall whatever we had discussed in the last class. We discussed about critical section problem. Basically, the problem is we should not allow multiple cooperating processes to enter into their critical sections at the same time. That's the critical section problem. And we discussed about one of the software solutions for that and the hardware supported instructions which are available. Peterson solution is a software solution which meets all the requirements to qualify as a solution for critical section problem. That is, it achieves mutual exclusion, progress, and bounded weight. Unfortunately, this solution cannot be used when there are multiple cooperating processes in the system. This is only proposed for two processes, assuming that there are only two processes in the system. Of course, cooperating processes. Then we discussed about some of the hardware supported instructions, and these hardware supported instructions have to be run atomically. Unfortunately, the problem with these hardware supported instructions is that they achieve mutual exclusion, whereas they don't guarantee progress and bounded weight. So in today's class, let us discuss about one more solution to the critical section problem that makes use of test and set instruction and meets all the requirements. It achieves mutual exclusion, progress, and bounded weighting. Now this algorithm uses test and set instruction which could be atomically executed by disabling the interrupts. Now this is a solution for critical section problem when multiple cooperating processes run concurrently in the system. Okay, and as I told you, it satisfies all the critical section requirements. I'm again telling they are mutual exclusion, progress, and bounded weighting. I hope you remember all this. With that assumption, I'm going to continue. This algorithm assumes that all the cooperating processes are going to share these data structures: an array of n elements, where n is the number of processes that runs concurrently. All the elements are of type boolean. That means they can either hold true or false, and one more variable lock, which also of type boolean and can hold true or false. Initially, all the elements of the array are set to false, and also the value of lock is set to false. Structure of a process looks like this. This entire section is the entry section, and this entire section is exit section, like we discussed in one of the previous classes. uh, the critical section problem can be effectively handled if there is going to be an entry section before a process gets into the critical section, and after it comes out of the critical section there is going to be an exit section where the process tries to allow other processes to get into the critical section. The other part of the code is called as the reminder section. Now, any process which is willing to enter into the critical section makes, let us say, process PI, which is trying to enter into the critical section, makes waiting of I is equal to true. And this key is a local variable. It also makes key is equal to true. Here we are making use of another variable lock. As I told you earlier, the lock value is also equal to false, and all the elements of this array are initially set to false. Now PI is making that true in order to show its intent to enter into the critical section. Now if this PI happens to be the first process that is trying to enter into the critical section, it looks at lock as false. So therefore, when it executes the test and set instruction, if it has to execute the test and set instruction, then both these conditions should be true. That is, waiting of I should be equal to true, that it has made true, and its local variable key is also true. So it is allowed to execute test and set instruction. Because the value of lock is false, the test and set instruction returns false and makes lock is equal to true. Okay, so therefore this condition fails, and the PI uh, will enter into the critical section. Before that, now its waiting is over, therefore it makes waiting of I is equal to false, and it goes to the critical section. Okay, so this section I'm going to explain little later, but while coming out of the critical section, it will select another process which is waiting for entering into the critical section to enter into the critical section here, that we have written here. And if the selected process again happens to be the same process, then it will make the lock is equal to false, so that some other process which first could acquire this lock can go into the critical section. I'll discuss about these things in detail. So like I said, this is a solution for multiple processes. Let us assume that there are processes 0, 1, 2, 3 and 4 are concurrently running. Let us assume that I is equal to 0, and it is the one which is making an attempt to get into the critical section. Now this will be successful in getting into the critical section, because if this happens to be the first process to see lock as false, our assumption is that now no other process has seen lock as false, so it will get into the critical section as I explained, right? Because it makes waiting of I is equal to true and key is equal to true, so and sees the lock value as false, it could enter into the critical section. But before that, it says that its waiting is over by making waiting of I is equal to false. Now see, suppose this after that, suppose this 3 wants to enter into the critical section. What this 3 would have made? This would have made waiting of 3 is equal to true. Okay, waiting of 3 is equal to true, and its local variable key is equal to true. Let me just write T. T means true. Okay, now let's see what happens if it is trying to enter into the critical section. Let's first try to understand whether mutual exclusion exclusion is achieved. So what is mutual exclusion? Though there are 5 processes here in the system, at any given point of time, only one process has to be there in the critical section. So that we'll have to ensure. Now we have one process which is there in the critical, already there in the critical section. Now P3 is also trying to enter into the critical section. Now let's see whether P3 is also allowed to enter into the critical section at the same time. Okay, now, okay, because P3 has made weighting of 3 is equal to true and key is equal to true, this is allowed, this process is allowed to execute the test and set instruction. What is the value of lock? Lock value is made true by PI while entering into the critical section. So therefore, this process P3, after it executes test and set instruction, it gets true as a value for key, and it has made weighting of 3 is equal to true. So therefore these two conditions are true. It will spin in this loop. That means it will execute test and set again and again. It sees lock value as true and it will get stuck in this loop, right? So this process is not, P3 is not allowed to enter into the critical section. The same argument holds good for other processes if they are trying to enter into the critical section. So hence we can say that this algorithm successfully achieves mutual exclusion. Now let's see whether there is going to be a progress or not when multiple processes makes a request to enter into the critical section. Okay, now P0 is already there in the critical section. P3 is the one which has made a request to enter into the critical section. Now we have to understand whether P3 is allowed to enter into the critical section or not. There will be a progress or not. Okay, so yeah, so you can also slightly modify this problem. You can also assume that this P4 will also try to enter into the critical section uh, along with P3, and it will also make weighting of 4 is equal to true and key is equal to its local variable key is equal to true. So which will be allowed to enter into the critical section? Now you look at this statement. We had assumed that the value of I is equal to 0. So therefore what happens to the value of j? J will be is equal to 1 modulus of n, because we, in a round robin fashion, we have to come back to the same process. So therefore I've used modulus of n here. So the value of j will be equal to 1. Now is this the process which goes into the critical section? No, because it is not having any intent of going into the critical section. Therefore it cannot participate in the selection also. So therefore what happens? It this while loop is executed. The first condition is true, j is not equal to I. That is true because I is equal to 0. Now j is equal to 1. What is the second statement? That is not weighting of j. That means the process P1 has not shown any interest to enter into the critical section. So weighting of 1 will be false. Not of that is true. So therefore both are true. Hence this statement is executed. That is j is now incremented and it becomes 2. And again the while loop is executed. J is not equal to I. Yes, that is true. And weighting of 2 is again false. So that not of that is true. Therefore this statement is again executed. Now what happens to the value of j? Now j becomes 3. Right? Now this is a process which has shown interest to enter into the critical section. Now you see here what happens. J not equal to I is true, whereas not of weighting. J has made, that is this P3 has made weighting of 3 is equal to true. Not of that is false. So therefore the control comes out of the loop. This you have to understand very carefully. it comes out of the loop and makes weighting of j false, that is weighting of 3 false. That's because j is not equal to I. The moment weighting of j is made false, now this P3 would have got stuck in this loop because both the conditions were true. Now what happens? Weighting of j becomes false. So when it becomes false, it will not execute this instruction. It will directly go here. It is saying that my wait is over. I am now going into the critical section. So it makes weighting of I is equal to false once again. It is already false, but it again writes false too. That will not hamper the working of this algorithm and enters into the critical section. The point that I am trying to make here is that now P3 is allowed to, because P3 is first in this order. If you take the order of requests, P3 has made the request first compared to P4. So therefore P3 is always given priority over P4. So P3 is allowed to enter into the critical section. So there is a progress. We have proved that there is mutual exclusion and there is progress. Now you must be wondering why this lock is equal to false. If yeah, okay. Now take the same example 0, 1, 2, 3, 4. Okay, let's assume this has gone into the critical section and no other process is willing to enter into the critical section. But this PI should give fair chance to other processes to get into the critical section. So what happens after this comes out of the critical section, J becomes 1, but process 1 is not interested, so it becomes 2. Process 2 is also not interested. It becomes 3. 3 is also not interested. It becomes 4. That is also not interested. Now you look at this, I have put the modulus of n. Now j value becomes 0. The moment j value becomes 0, now this condition is false. J not equal to I is false. J is equal to I. So therefore it will execute this if statement. Whether j is equal to I? Yes. So it makes lock is equal to false. It will not make waiting of some other process false because no other process is waiting. So therefore it makes the variable lock's value as false and goes into the remainder section. Now if somebody now at this point of time wants to enter into the critical section, it may do so. So that's the reason this is written. That is, if the turn again comes back to the same process before entering into the critical or holding the lock, because it has to go to the remainder section, it releases the lock. So that's the idea behind making lock is equal to false when j is equal to I. Let me demonstrate that bounding weight constraint is also met. The argument that I made to demonstrate that the progress requirement is met, the same arguments holds good here also. Okay, say a process P naught coming out of the critical section, this will select the next process that has to go into the critical section and exit out of critical section, right? It goes to remainder section. So thereby, for example, if you take the same set of processes, for example, now this process was there in the critical section and this process would like to enter into the critical section. So in a round robin fashion, that is this 4 is selected to enter into critical section. If it is not interested, then 0 is selected, then 1 is selected, then this 2 is selected. So that means this 2 will only wait for, that is at the maximum, any process will wait for n minus 1 turns to get into the critical section. So this is a bound on the waiting time of the process which is making the request. So therefore, hence this bounded wait or bounded waiting requirement is also met. So here what I have discussed is another solution which makes use of hardware instruction test and set, meets all the requirements of a solution to a critical section problem, that is mutual exclusion, progress, and bounded waiting. Not only that, this is a solution for when multiple cooperating processes are running concurrently in the system. So therefore, this can be accepted as a solution for the critical section problem. So therefore, we discussed Peterson's solution and this solution, and both qualify for becoming perfect solution for the critical section problem. Okay, though these solutions are effective, we cannot use Peterson's solution because that is meant for two processes, and these are hardware supported instructions, and it becomes difficult for the programmers to use these instructions. The solution becomes quite complex. So therefore, in order to give an easy option for the programmers to solve this critical section problem, uh, two synchronization tools have been developed. They are semaphores and monitors. Let me first discuss about semaphore. What is a semaphore? Semaphore is a synchronization tool. Let me discuss about it in depth, and then I will take up monitors and see what monitors are and how they solve the critical section problem. Let me define semaphore first. A semaphore is an integer variable that, apart from initialization, is accessed only through wait and signal. Now you might be wondering now, just an integer variable, how this could solve the problem of critical section. We will take a look at it with an example and see how this helps us in process synchronization. Before that, you have to understand clearly what is wait operation and what is signal operation. Wait is an operation performed on the semaphore. This here, this S is a semaphore. It checks the value of semaphore if the value of semaphore is less than or equal to 0. That means if it is negative or equal to 0 and it does nothing, otherwise wait decrements the value of semaphore by 1. That means if the value of semaphore is 1, then it makes it 0 after the execution of wait. Similarly, this signal will simply increment the value of semaphore by 1. So if the value of semaphore is 1 and if signal is executed, the value of semaphore becomes 2. So this you have to understand clearly to understand how semaphore could be used to synchronize the execution of cooperating processes. Okay, the uses of semaphore is very interesting. The semaphore could be used as binary semaphores. As the name says, the semaphore can have, let's say, S is a semaphore, can have two values, either 0 or 1. So therefore, you can call the semaphore as a binary semaphore. Sometimes this kind of a semaphore is also called as mutex lock. Okay, so let's see how this mutex lock can be used to achieve mutual exclusion in a while. Before that, let me tell you that another type of semaphore is counting semaphore. Okay, in case of counting semaphore, the semaphore can take any integer value. It could be 10, it could be 15, or any integer value. And how semaphore, counting semaphore could be used? It could be used to control access to a given resource consisting of a finite number of instances. Let us say that there are 7 printers connected to a computer system, and the processors are sharing these printers. Okay, now every time a process makes a request for a printer, it will execute what is known as wait. Okay, so the value of semaphore is initialized to 7, meaning there are 7 instances of this resource, this kind of resource, that is printer. So every time a process executes wait, the value of semaphore is simply decremented. That is, when P0 is trying to use a printer, it executes waits and decrements it by 1, becomes 6. Let's assume there are multiple processes trying to use the printer. Every time it tries to use the printer, it decrements the value of semaphore. So value of semaphore goes on getting reduced by 1 till it becomes 0. If the value of semaphore becomes 0, what is the meaning of that? Now you don't have any more instances of this kind of a resource to allocate to the processes. So after that, any wait executed by a process will make the process to wait as per our definition, is it not? So it has become 0. So any process, you know calling wait, the value of semaphore is checked because it is equal to 0. So therefore the process will wait in the loop. It is the semaphore will not decrement the value of the semaphore, right? Sorry, the wait operation will not decrement the value of the semaphore. Okay, now what happens, the process P0 which was using this printer is done with the printer, and it releases the printer to the pool of printers. So while it is releasing, it executes a signal operation. So according to our definition, what signal does, it simply increments the value of semaphore by 1. So it makes the value of this S is equal to 1, which means there is one printer available for use. Like that, after every process finishes their work with the printer, they execute the signal operation, and the value of S goes on getting incremented, so till it becomes 7, right? So this is how we can make use of semaphores to synchronize the execution of processes, or to control the access to a given resource having finite number of instances. So this is about the counting semaphore. Now let us take an example and see how binary semaphore could be used. This I should have discussed first, but it will take little time, so therefore I finished discussing about counting semaphores. Now let us discuss about the use of binary semaphore by taking this example. All the cooperating processes, be it P0, P1, P2, will have a similar structure. That's our assumption. And the initial value of mutex is made 1, right? It is made 1. So all of these processes are seeing the value of mutex as 1. If some process wants to enter into the critical section, let's say this process P1 wants to enter into the critical section, it will do this operation waiting, sorry, it should have been wait operation on mutex. So what will happen to the value of mutex? Because the value of mutex is greater than 0, so it is simply decremented, mutex becomes 0, and P1 is allowed to enter into the critical section, right? Now let's see if P2, when P1 is in the critical section trying to enter into the critical section, it sees the value of mutex as now 0 and it performs wait on mutex. Because the value of mutex is 0, it cannot decrement its value, so it will wait. Okay, it is stuck in that wait loop, right? So P2 is not allowed to get into the critical section. Hence, the mutual exclusion is achieved. Only when the P1 comes out of the critical section, it executes signal which makes the value of mutex 1. It increments the value of mutex by 1. Only then this process which is stuck in the loop, okay, now sees mutex as no 1. That means it has a value which is higher than the 0. So that's when it makes its value 0 and enters into the critical section. So that's how you can make use of binary semaphore for process synchronization or synchronizing the execution of multiple processes. See, another use of semaphore, you can do a kind of scheduling of statements which are there in different processes. Here I have considered two processes P1 and P2. P1 has statement S1 and P2 has statement S2. Now we want that S1 should get executed before the S2. Now for this, can we use the semaphore? I have now here used a semaphore called sync and its value is initialized to 0. Now you know that during scheduling any one of these two processes could be picked up for execution. Suppose if P2 is picked up for execution, then what will happen? So wait is performed on sync because the value of semaphore sync is equal to 0. The process P2 has to wait. It will start executing the while loop. It gets stuck in the while loop, and after some time it is taken out of the CPU, right, by the scheduler, and P1 is picked up for execution. When P1 is taken for execution, it will first execute S1. Okay, it executes S1. That's what we want. Okay, we want S1 to happen before S2. After that, this process P1 will execute a signal operation on the semaphore uh, sync. So what happens to the value of sync? It was 0, now it becomes 1, right? It becomes 1. Now this process P2, if it is now again scheduled for execution, it executes this while loop, and inside the while loop it sees the value of this semaphore as 1, which is greater than 0. Therefore it will simply make this value 0 and you know goes into the next line, and S2 gets executed. That's how you can force execution sequence of statements of different processes with the help of semaphore. So these are all the advantages or usages of semaphore. You can use it as a binary semaphore for achieving the synchronization among the concurrently running processes, or you can use counting semaphore to control the access to particular kind of resource having multiple instances, or you can use this to this kind of a synchronization problem, that if you have something like execute statement S1 before the S2, you can do so with the help of a semaphore, which I have now demonstrated here. So I have also used pthread library. Pthread library has got implementation of semaphore. I have written some C programs. I will demonstrate how semaphores can be used for mutual exclusion and for this kind of synchronization issues. Okay, before I demonstrate the program, C program that I have written, which uses the semaphore library, which is present in the pthread POSIX pthread library, I would like to discuss about one major issue that is there with this kind of a semaphore definitions. If you remember, um, this is the definition for wait, and this is the definition for signal. So you look at this carefully. When the value of s is negative or 0, now what the process which is executing this wait operation will do, it will end up wasting the CPU cycles, right? CPU cycles, because it is going to execute this while loop again and again, which is called as busy wait, or it can also be called as spin lock. Okay, why this is an issue? Busy waiting wastes a lot of CPU cycles that some other process might be able to use productively. So what is happening? The process spins in the while waiting for the lock, right? And wastes a lot of CPU cycles which could have been used by some other process. So what is the solution? Is there any means of pushing that process which is busy waiting to a queue, and giving the CPU to some other process to make use of the CPU? So that's the solution for busy waiting. I hope you have understood what is busy waiting or spin lock. It is when a process is in critical section, if some other process tries to enter into the critical section, let's say context switching happens to this process which is trying to enter into the critical section, the process which has made the request will not be allowed to enter into the critical section because some other process is already there in the critical section. So what this process does, it is stuck in that while loop. It will execute that while loop again and again. So that is known as spin lock, or that is known as busy wait. It will not leave the CPU, it will occupy the CPU and execute the while instruction again and again. So this is the issue, or this is the problem. We are wasting a lot of CPU cycles which could have been effectively utilized. In the next slide we will see what is the solution for this and how that solution can be implemented by modifying the original definitions that we gave to wait and signal operations. Okay, what is the solution to spin lock or busy wait problem? Every semaphore is associated with a waiting queue. What is this waiting queue? I'll explain that in a while. Each waiting queue has two data items. One is the value of the sorry, not the waiting queue. Entry in the waiting queue has two data items. That is, one is the value of the semaphore itself, and another one is the pointer to the list of waiting processes. If some other process is already waiting on this semaphore, so there will be a pointer to that list. That list will have multiple processes waiting on this semaphore or for this semaphore. This thing will become very clear when we take the example and understand. So here what we are trying to do is, instead of allowing the process P uh, waste CPU cycle because it is not allowed to enter into the critical section, we will have to change its state from running to blocked. So there has to be a mechanism of changing this state of this process from running to blocked. So what we do is that when we see this P is busy waiting, a block uh, you know command or block operation is invoked by this process, which will place this process into a waiting queue. So that is that this waiting queue corresponds to a particular semaphore, right? If one of such processes has to be uh, you know awakened or woken up for execution when some process P is done with the critical section, executing the statements in the critical section, the process can use wake up. So this wake up, as we told you, that there will be a pointer to a list which is having list of processes which are waiting on this semaphore. So one of the processes, that is the process which is present at the head of this list. This can be a simple first in first out list. So whichever process is waiting at the head of this list can be released from that waiting queue and put into ready queue, and the scheduler can pick up this process from the ready queue as per the scheduling algorithm used. So that means we are changing its state from waiting to ready. Please understand what is that we are trying to do is that instead of allowing a process P to waste CPU cycles, block it, send it to a waiting queue, and it will remain in the waiting queue till some other process which was there in the critical section completes its critical section. While coming out, it will woke up one of the processes from this waiting queue. So that is what is the solution to the spin lock or busy waiting. Now let's see how this can be implemented by modifying the definitions that we had given to wait and signal operations. Okay, now look at the structure of the semaphore. Now the semaphore is not just an integer value. It is now defined as a structure which has got two elements. One is its value, integer, and a pointer to a process. It is a pointer to a list of processes. So that's how we have modified the definition of the semaphore. Semaphore is not just an integer value, it is an integer value and also has a pointer to a list which contains the processes which are waiting on this semaphore. Now let's see how to use the semaphore, this modified semaphore. We have to modify the wait and the signal operations. Now the wait operation looks like this. Okay, S is a pointer to the semaphore. When we execute wait, wait will simply decrement the value of semaphore by 1 before inspecting the value of the semaphore. So what may happen here, now the value of semaphore might become negative, which we will see when it is going to become negative. Okay, after decrementing the value of semaphore by 1, it is going to look at the value of semaphore. If it is less than 0 after decrementing, then uh, the process is pushed to a waiting queue, and its pointer to its PCB is added to this list. Okay, how it is pushed to the waiting queue? By executing a a command or an operation block, right? So any process which changes the value of semaphore to negative will go into the waiting queue and wait for, which means that some other process is already there in the critical section. Suppose if the value of semaphore is, let us say, 12, it means that there are 12 processes which are waiting for entering into the critical section. That's the meaning. Okay, so here this is also allowed. Negative value to the semaphore is also allowed, which we did not accept when we gave the original definition to wait and wait operation. Now the what is the modification that is done to the signal? Again, what is passed to this operation? A pointer to a semaphore. Semaphore value is first incremented. Suppose if the value of semaphore is 12, there are 12 processes in the waiting queue. Okay, so the value of semaphore is incremented by 1, it becomes minus 11, and if it is less than or equal to 0, means that waiting processes are there in the waiting queue. So remove a process P from that waiting queue, change its state from waiting to ready. Okay, and that is done with the help of a wake up operation, wake up of P. Okay, so this is a process which is present at the head of the waiting queue. So this is removed from the waiting queue and you know mm, allowed to enter into the critical section. So this solution will address the problem of spin lock, or it will address the problem of busy waiting. Okay, so as soon as some process waits to enter into the critical section, that process is simply pushed into the waiting queue. At any given point of time, the value of S will tell us how many processes are there in the waiting queue. If S is what? Semaphore. If S is equal to 0, no process is there in the waiting queue, right? Waiting to enter into the critical section. So that's how we can make use of the modified wait and signal operations to achieve process synchronization among the concurrently running processes. So that's how we could use a semaphore as a synchronization tool. Now next I am going to demonstrate how the semaphore tool that is defined in the pthread POSIX pthread library could be used to synchronize the execution of processes. Okay, so I will not be able to do that in this class. In the next class I will start with that demonstration and discuss about various classical synchronization problems or issues that are there, and how those problems can be effectively handled by using semaphores. So thank you very much.